Okay, so last time we were talking about equivalence relations. What was the point of equivalence relations? For various reasons, in practice, we need to treat different objects, we want to treat different objects as if they're the same. So we set them to be equal, whatever that means. They're not really equal in the sense of equality. They're distinct, but they're equivalent under certain relation. And we talked about equivalence classes. And then we defined the notion of a partition. And we saw that for every partition there's an equivalence relation, and for every there's an equivalence relation there's a partition. So let me state that again. Let E be an equivalence relation on a set X. Let's make this non-empty. Then the set of equivalence classes of this equivalence relation is a partition of X. What does this mean? This means, remember, the elements of this guy are disjoint. Their union is all of X, okay? And these are subsets of X. Each element of this is a subset of X, okay? So we had that. And conversely, given a partition S of a set X, the relation E sub S defined as follows. Two elements of X are related if only if there exists an element of this partition to which both these guys belong. This relation is an equivalence relation. Okay? So we proved this last time, I believe. It was the last theorem, and I just did the transitivity, and I gave as an exercise to prove that this is reflexive and symmetric. Okay. So let me state the following theorem. I'm not going to prove this. It's not difficult to prove. We already proved some of it. Sometimes people call this the fundamental theorem of equivalence relations. I don't want to call it that because then it's going to sound too important, even though it's not that important. So let X be a non-empty set. Then the function f from the set of equivalence relations to the set of equivalence relations on X to the set of partitions on X given by partitions on X given by f of E goes to X quotient E is a bijection whose inverse is given by this. So we have a set. We start with an empty set. We have equivalence relations on this set, and we have partitions of this set. For every equivalence relation, I have an associated partition, and for every partition, I have an associated equivalence relation. The theorem tells you that there's a one-to-one correspondence, like these, if you think of these operations from the set of equivalence relations to the set of partitions, these are inverses of each other. And it says actually, this theorem says something more. it says the following. You have a set of equivalent solutions, you have a set of partitions. There's a one-to-one correspondence between these sets. There's a bijection between the set of equivalent solutions on a set and the set of partitions of that set. And a bijection is given by this. You take any equivalent solution, you look at the corresponding quotient set. This is a partition, so this is a bijection. If it's a bijection, it has an inverse. What's the inverse? The inverse is given by this. You start with a partition, you look at the associated equivalent solution. So that's the inverse of this, okay? Is this understood? Are you sure? Is that your final decision? Good. Now we're gonna, I don't remember whether we're gonna use this a lot, but this is somewhat important. It tells you that there's a correspondence between equivalent solutions and partitions, and you can jump from one to the other and come back in a natural way. Now, let's talk about a very important concept, namely the concept of a transversal of an equivalent solution. Now, in practice, what happens a lot in mathematics is that okay, what's the point of equivalent solutions? You want to treat objects as if they're the same. So you put all these objects which are considered to be same to somewhere, okay? So you have your equivalence classes. Then at some point, you need to choose one element from each equivalence class. For example, I'm not sure whether you know this, but like there's this famous theorem called the Banach-Tarski paradox. You can take a ball, split that into 5 pieces, move these pieces around just by rotations and translations, put these back, and you get 2 of the same ball. You basically double ball, okay? So you have 2 balls and each of those are identical to the original one. If you look at the proof of this, you'll see that at some point there's an equivalence relation and you just choose one element from this from each equivalence class, okay? Or if you know measure theory, which I taught last semester, but I don't think any of you has taken that. So we constructed an unmeasurable set. At some point, we did the following. We defined some equivalence relations, which was called the Vitali equivalence relation. At some point, we chose one element from each equivalence class. So choosing one element from each equivalence class, this happens a lot in practice. So why can we do that? Why is this justified? It's justified because of the theorem I'm going to state over here. Let me first give a name to the set I'm going to construct. Let X be a set, and I'm going to work with non-empty sets. Well, I can work with any set. And E be an equivalence relation on this set X. A subset of X, I'm going to call this T, is said to be a transversal if the following happens. Transversal if for every element of X there exists a unique Y. In the notes, there's a typo over here if you're checking the notes. So I'm going to fix those, okay? I'm realizing the typos because I'm rereading this again for the second time. I'm going to fix those later. So in the notes, it doesn't say unique. It's supposed to be unique. There is a unique Y in T such that Y belongs to the equivalence class of X with respect to E. So what's the transversal? This is your set X, okay? You define some kind of equivalence relation on X. I don't care what it is. It can be the identity equivalence relation. It can be the full equivalence relation, which is the equivalence relation obtained by just making everything equal. It can be that. It can be any equivalence relation. So you have equivalence classes. Obviously, in order to have equivalence classes, you need to have a non-empty set. So pretend that X is non-empty. So you have equivalence classes, okay? So these are my equivalence classes. So these elements are all equal to, they're equivalent to each other. They're not equal, they're equivalent to each other under this equivalence relation. Because the quotient space is a partition, There are no more elements in X. Every element is contained in some equivalence class, namely the equivalence class of itself. So this is all of X. Now, a transversal is a set which intersects each equivalence class at a single point. So a transversal is a set such that for every X, you have a unique element in T which is in the corresponding equivalence class. So you choose one element from each equivalence class, okay? So in practice, when you do that, you basically claim the existence of a transversal. Like when I'm going to choose one element from each equivalence class, you're just talking about a transversal. Is this understood? Is the picture understood? You're choosing one element from each equivalence class. Okay. Now, we just defined what it means for a set to be a transversal. But the question is, do these actually exist? I mean, I can talk about flying dogs with unicorn hats. Just because I can talk about these doesn't mean that they actually exist. So, do transversals exist? Lemma, let X be a non-empty set and E be an equivalence relation. E be an equivalence relation on X. Then there exists a transversal T for E. Maybe I should say that T is said to be a transversal for E because it depends on the equivalence relation, right? Now the proof is actually very simple. It's done as follows. As X is not empty, the set X quotient E is a non-empty set whose elements are non-empty. Now there are too many non-empties over here. Let me explain this. So where was the definition of this? Okay, let me put it over here in a box. If X is a non-empty set, then there is some X. So X quotient E is non-empty. Moreover, the elements of these guys are non-empty because they're equivalence classes. And equivalence classes, by definition, non-empty. Right? Okay. Now, I have a non-empty set whose elements are non-empty. What can you tell me? Remember the lemma we did right after the axiom of choice. By a consequence of axiom of choice, by a consequence of AC, we defined AC in a different way, but right after I defined axiom of choice, remember last time I recalled the axiom of choice. It was over here, then I proved the lemma, which was over here. Okay, so that lemma said, if you have a set, non-empty set, whose elements are non-empty, then there exists a function such that, so this is a non-empty set whose elements are non-empty, so there exists a function from here to here, such that f of u is in U for all u in X quotient E. This is simply by axiom of choice. Indeed, this is equivalent to axiom of choice. Remember that lemma? I told you that it's equivalent to axiom of choice. Anyway, let's understand this object. What is the union of this collection? What's the union of a single set? It's the union of its elements, right? It's the set consisting of elements of this. You take all these equivalence classes together, you take their union. What do you get? You take all these equivalence classes together, you take the union of this. What do you get? You get X. So I have a function which does the following. For each equivalence class, my function chooses one element from that equivalence class. I have a function f which does the following. It takes this equivalence class to an element of that equivalence class. Okay? So if I look at the image of this function, this is a transversal. Maybe I should redraw this. These are my equivalence classes. I have a function f which takes each equivalence class to an element of that equivalence class. Okay? I look at the image of this function. I look at the range. The range intersects every equivalence class. Why? It's by definition. For every equivalence class, the range intersects it. It contains some element. And just because this is a function, it can intersect every equivalence class at a single point. Pretend that there's another equivalence class here such that this is also mapped to this. What would happen? Well, this is supposed to pick an element from, like, call this u, call this v, f of u is in u, f of v is in v, but then u equals v automatically. Sorry. Pretend that u equals v, assume that that's the case. No, I'm not making sense. Let me rephrase. I'm kind of tired, so let's say that you have two equivalence classes u and v such that their images are the same. Okay? What can you tell me? This element belongs to this equivalence class and this equivalence class. But two equivalence classes are either the same or they're disjoint. So they're not disjoint. They contain a single element, which is inside both of these. Therefore, they're the same. So we're not using the fact that f is a function. We're using the fact that two equivalence classes are the same. They're either exactly the same or they're disjoint. Okay? The point is, the image is a transversal. Okay? And transversals simply exist by axiom of choice. It is a theorem that without axiom of choice, you cannot prove this. It is a theorem that you cannot prove this without axiom of choice, okay? If you refuse axiom of choice, there are models of that set theory which does not satisfy that theorem. Namely, there are equivalence relations without transversals. Now, why is the existence of transversals important? Because, as I said, I already explained that they're used a lot in practice. And sometimes they do magical things, one of which we're going to see in a second. Okay, some of you might have heard this puzzle before. Even if you did, pretend that. Sorry for this. I think I created a giant noise for listeners. Now that some of our listeners have become deaf, we can continue. So, this is a cool puzzle, so when I finish, act surprised, okay? And in the notes, I described this whole puzzle in the setting of Game of Thrones. You might have read that. Here, I'm not going to do that. So we have infinitely many prisoners. Okay? So at the beginning, they're sad because they're going to be executed. At this point, I should add some remarks. We haven't defined what what it means for a set to be infinite. You don't know what infinity is. You don't know what countably infinite is. Like, we haven't learned this. We haven't learned those in this course. However, you have an intuitive understanding of infinity, right? And I know by a fact that you all know what countably infinite means from like first year courses. So I'm going to pretend that you know these concepts, even though in this course we have not covered these. So we have infinitely many prisoners. Indeed, countably infinitely many prisoners. So I can enumerate them by natural numbers. So these prisoners are going to be executed. Okay? Because, I don't know, there's some cruel king who wants to execute these guys, okay? But the king likes puzzles, so he creates a puzzle for these infinitely many prisoners to solve. Every prisoner is randomly given a hat, okay? Which is either red or blue. I want to add more prisoners. Okay, so let's make this red and let's make this blue. The prisoners are supposed to guess the color of their hats, but there are some restrictions. First of all, the prisoners can only see all the prisoners in front of them. So they're just like, they're lined up on a straight line to infinity. They go like this, okay? They have a hat. They're not allowed to communicate in any way. So they're just randomly given some blue or red hat. They're just facing this direction. They can see all the prisoners in front of them, all the prisoners, infinitely many prisoners in front of them, but they cannot see anyone behind, or they cannot look at their own hat. Otherwise, it would be a trivial puzzle. Okay? Now, obviously, it is impossible for these prisoners to know all the colors of their hats. Okay, here's the puzzle. I phrased it so badly. Let me go over this. The puzzle consists of finding a strategy so that every prisoner knows the color of his hat. Okay, so everyone wants to guess the color of his hat. Obviously, this is impossible to solve if I require that all prisoners should do that, because here's the first prisoner. He has no information about his hat. There's a 50% chance that he's going to get it right, but he can be executed right after the guess, okay? So the king is not that cruel, so he somehow weakens the condition. He says that, okay, I don't want all the prisoners to know the colors of their hats, but I want all but finitely many of them to do that. What all but finitely many means? Each prisoner is asked the color of his or her own hat, okay? So they're just saying it in order, okay? Or they're saying it simultaneously. They're asked the question, they're just writing it on a piece of paper so that the others can't hear it, just handing it to the king. So they're just guessing at once the color of their own hat. If at the end only finitely many of the prisoners guess it wrong, they all live. If infinitely many of them makes a wrong guess, they are all executed, okay? So in order to win the game, in order to survive, only finitely many of these guys should guess the colors wrong, okay? The question is, does there exist a survival strategy? Okay, like, can the prisoners out? And all these rules are explained to the prisoners like one night before this game, so they can come up with a strategy. So they can do something like this. Okay, let's say that here's our strategy. All of us are going to guess red. Everyone will say red. They might survive if all the hats are red, but the hats are like distributed randomly. So it's not guaranteed that they're going to survive. So they should come up with a better strategy. They can say that, okay, the even guys should say red, the odd guys should say blue. Depending on the situation, they might survive, but not likely, because the hats are distributed randomly. I want a strategy which works all the time. So what are they supposed to do? Here are some assumptions. You can assume that, we will assume that all the prisoners have infinite amount of memory. So they can see all the prisoners in front of them, and they can also memorize all the colors at the same time. So the brains of these are super smart guys whose brain can handle infinite amount of information. So they're gonna die if we don't come up with a strategy. But we can actually come up with a strategy so that all these guys survive, so that now they have smileys. They will survive. And they will survive only because of this lemma. Okay? We're going to prove that there exists a survival strategy for this game. So, just to make sure that everyone understood this, let's go over this. Infinitely many prisoners facing this direction. They can only see everyone in front of them, but not themselves or the other guys. They're not allowed to communicate in any way. They're randomly given some hat, red or blue. They're simultaneously asked the question, what's the color of your hat? And they're just writing in a piece of paper, so no one hears what the other one says. Their brains can handle infinite amount of information, so they can just memorize all that data in front of them. Question is, find the strategy so that only finitely many of the prisoners will make a mistake. All the time, like regardless of how the hats are distributed. So, does there exist a survival strategy? Theorem, yes. There exists a survival strategy for the infinitely many prisoner problem. Proof. Okay, I'm going to use this part of the board as well. First of all, just the statement should be surprising to you, like that there exists a survival strategy. Here's the reason. They have no information whatsoever about the color of their hat. They can only see the guys in front. And because the hats are distributed randomly and independently, this color has nothing to do with those colors. So how on earth those colors, that information I can access, will tell me something about the color of my hat, which is a completely independent piece of information. Like, there should be a probabilistic strategy, but I'm claiming that there exists a deterministic strategy. It works all the time. So this should be, by itself, very surprising. And it is, I think. So act surprised now. Okay, good. We can continue. I saw the face. So what we're going to do is, we're going to first make this problem mathematical. Because this problem is not mathematical as is. All the objects in our universe are sets, and these are not sets. These are prisoners. And these are not sets. These are hats. So let's make the problem mathematical. We are going to associate prisoners with natural numbers. Okay, so this prisoner is this natural number, this prisoner is this natural number, and so on. We're going to associate these colors with zeros and ones. So I'm going to declare this to be 0, I'm going to declare this to be 1. I'm going to declare this to be 0, 0, 1, and so on. Now, let's say that I distributed the hats. I want to somehow mathematically describe the situation. After associating these guys with natural numbers and these hats with zeros and ones, I can just describe the whole situation as a function from natural numbers to 0, 1, okay? So by associating prisoners with natural numbers, again, we don't know what natural numbers are at the moment. Pretend that we know it, okay? We're going to see this like in a couple weeks. By associating the prisoners with blah, blah, and the colors red and blue with 0 and 1, we can describe possible scenario by a function from natural numbers to the set 0, 1. Now, I'm going to call this set, I'm going to call this doubleton consisting of 0 and 1, 2. Okay? You're going to understand why I'm doing that later. So, a possible scenario, and when I say a scenario, I mean you distribute the hats and you see some scenario. Yeah, you see some scenario. That's a possible outcome of this puzzle. Not the outcome, but, well, you understood what I mean. So, after doing that association, this scenario can be represented by a function from natural numbers to 0, 1. For example, this scenario corresponds to the function which takes 0 to 0, 1 to 1, 2 to 0, 3 to 0, and so on. Okay? Now, consider the equivalence relation E defined on this set. What is this set? Anyone remembers what this is? This is the set of functions from natural numbers to 2. So this is the set of all such functions. I'm defining an equivalence relation on this set. I'm doing it as follows. Two functions are said to be equal, they're said to be E equivalent, if and only if they agree after some time. What do I mean by this? Two functions are said to be E equivalent if and only if there exists some natural number such that after that natural number, these functions take the same value. Another way of describing this is as follows. Look at this sequence, 0, 1, dot, 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 dot. A function from natural numbers to 2 is simply a sequence whose entries are 0 and 1, right? If I have two such functions, this is a function from natural numbers to 2, this is a function from natural numbers to 2. I'm declaring two such functions to be equivalent if and only if their tails are the same. For example, pretend that these guys are the same after this index. You see, they're different over here. But pretend that they're the same after 0, 1, 2, 3, 4. Pretend that after 4, they're the same. So they take the same values after 5. Then I declare these to be equivalent. Now check that this is an equivalence relation. This is an exercise. Indeed, last year this was like a 5-point question in part A of some exam question, okay? So check that this is an equivalence relation. By the previous theorem, or was it a lemma? I think it was a lemma. No? Theorem? Okay, let's call it a theorem. There exists a transversal for this equivalence relation. Transversal for E. Okay, this exists. Here is my strategy. Remember, the prisoners can memorize an infinite amount of information. So they can memorize the transversal by assumption. I just made them infinitely much smart, okay? So they're very smart. They can memorize the transversal. Here's their strategy. Here's the survival strategy. prisoner n, okay, for each natural number n, prisoner n constructs the function, I'm going to call it what? Alpha. Which codes the color of hats, assuming that all the colors he doesn't see are red, okay? So I'm prisoner number, let's say, 3. I don't see these 4 hats, but I see all the other hats. So what I do is this. I simply assume that all the colors I don't see are red, okay? So I'm assuming that my hat is red, everything behind is red, and I'm looking at all these colors. So I code this into a function from natural numbers to 0, 0, 0. So it's like I've constructed a function which takes the values 0, 0, 0, 0. Then for the colors I see, I just simply code it. I simply code what I see. If I see blue, I put 1. If I see red, I put 0, and so on. So I just construct a hypothetical scenario. This is, I don't know what the actual scenario is. This is a hypothetical scenario. If I'm prisoner n, I know that the function I construct agrees with the actual scenario after n because I see the colors. But I'm just assuming that all the other colors are red. Now what I'm going to do is the following. Prisoner n guesses the color of his own hat as, here's the hypothetical scenario I constructed. This hypothetical scenario belongs to some equivalence class. My transversal intersects this equivalence class at a single point. So this is now either the singleton 0 or singleton 1. I'm just going to take the union of this. So this is now either 0 or 1. Okay? Now this is either 0 or 1. What am I guessing? I look at the hypothetical scenario. I look at the equivalence class of hypothetical scenario I constructed in my head. My transversal intersects it somewhere. I look at the intersection. Now this consists of a single element. Sorry, I'm not making sense. It's not either 0 or 1. This is a function. I'm supposed to evaluate this. Sorry. What am I doing? This is a function. Okay? Now, I guess the color of my own hat according to this. So I'm going to evaluate this function at n. Okay? Okay. I claim that this is a survival strategy. So, did everybody understand? Now this is 0 or 1. Sorry for that, I mixed it up. Did everybody understand the strategy? I construct a hypothetical scenario. I look at the equivalence class of that scenario. I intersect it with my transversal, which I memorized the night before. Now this intersection consists of a single element, right? It consists of a single function. Actually, this is like a single function. Let me write this completely mathematically correct. This consists of a single function, okay? Now, if I take the union of that singleton, I'm going to get a function. This is now the function which is equivalent to my hypothetical scenario and which is in the transversal. I evaluate this at n. So I guess the color of my own hat according to that. I claim that this is a survival strategy. Okay? We claim that this is a survival strategy. Here's why. Okay. Let G be the function which describes the actual scenario. So the hats are distributed. Every prisoner gets the color red or blue. So this is the actual scenario. This is what's happening in reality. This is the colors of the hats in reality, okay? Now, each prisoner is constructing some hypothetical scenario. But notice that that hypothetical scenario and this one are always E-equivalent. Why? Because the hypothetical scenario I'm constructing is like the tail of that function is the same as the tail of this function. The actual scenario and the hypothetical scenario I constructed can only disagree at the indices behind me, which means that all those hypothetical scenarios, all those alphas we constructed are actually equivalent to G, okay? So, let H be the unique function such that H is equivalent to G. Now, we chose we wrote down some sentence. Let's see whether this makes sense. I'm choosing one element from my transversal, and I'm saying that this is the unique function, blah, blah, happening. Why does this make sense? Why is this true? Why does there exist such a function? Because the transversal intersects every equivalence class, right? Look at the equivalence class of G. There should exist a unique element in the transversal which is in the equivalence class of G. So there exists such a function. It's unique, okay? Notice that all the prisoners make their guesses according to H. Now let's go over here. Prisoner N constructs this hypothetical scenario, which is equivalent to the actual scenario. And prisoner N guesses the color as this guy. Now, this alpha, this hypothetical scenario, is equivalent to the actual scenario, right? So this is actually the equivalence class of G, the equivalence class of the actual scenario. The hypothetical scenario I'm constructing is equal to the actual scenario. The unique element in the transversal, which intersects the equivalence class of G, is H. I chose H that way. H is the unique element in the transversal which is equivalent to G. So every prisoner guesses according to H. So somehow using this equivalence relation, I made every prisoner guess according to the same function. They all guess according to H. Now, as G and H are equivalent, there exists some natural number m such that for all natural numbers n greater than or equal to m, h of n equals g of n. Thus, all prisoners, well, thus prisoners numbered n for n greater than or equal to m guessed correctly. Now, all the prisoners guess according to age. But by definition, because h and g are equivalent, h and g agree for sufficiently large natural numbers. So there exists some m such that after that m, these values are the same, which means that except the first m prisoners, all the prisoners guess the colors correctly. So all of them survive, because only finitely many of them failed to guess the color correctly. Okay? Now, there are versions of these puzzles where these guys do not know the colors, where they don't know their number, okay? They don't know what position they are in. There are variations like they're extending in infinity to in both direction, okay? So you can make this with 3 hats. It doesn't actually matter, okay? They can extend in this direction. There are variations. All of them are solved via a similar trick. You just define some equivalence relation. You use some transversal to make a guess which is correct almost all the time, okay? So this puzzle has variations. I learned this when I was in my 3rd year, I guess, like when I was an undergrad student here. Like this, at the time and still, like this is really cool, okay? I mean, this puzzle seems impossible to solve. Indeed, ask your friends about this. Like, you know, there are puzzles where there are finitely many prisoners and they're guessing their colors except one of them may make an incorrect guess. They're like, you're using modular arithmetic or something like that. You guess the color. Those are basic puzzles. Ask these to your friends, okay? They will tell you that like this is impossible to solve, but then there's a solution. Except the solution involves some assumptions, like these prisoners are assumed to be infinitely smart, so that they can actually memorize the whole transversal, which is an uncountable set, whatever that means, which we have not learned. Yes?
I don't understand if the transversal is unique.
You mean it contains a unique element?
No.
Oh, the transversal is unique. No. There are uncountably many transversals because, okay, maybe I should, here's a very stupid case. Natural numbers say that 2 elements are equivalent if and only if they are both even, and 2 elements are equivalent if they're both odd, okay? How many transversals are there? You can choose 0 and 1, 0 and 3, 2 and 1, 4 and 3. There are infinitely many different transversals. Even in this case, uncountably many, okay? Next hour, I'm going to write down a very basic exercise regarding transversals so that you digest this concept. So let's have a 10-minute break, and I'll see you in 10 minutes.